Hi, I'm Bjorn Therese, and this is part 9 of my video series on process control. In this video, we'll discuss derivative action in PID controllers, but also mention how you can tune level flow and pressure controllers generically. I've made some additions to the app that allows me to simulate an alternate process to the heater and tank example. This new process is not a single first-order lag plus dead time, but contains some features that lend themselves to applying derivative action. To illustrate where we're going, I show the same disturbance response on this process with two different controllers, both tuned for the same level of stability or robustness. To the left is a PI controller with the best possible settings for disturbance rejection. To the right is a PID controller responding to the same step disturbance. The benefit of derivative action speaks for itself. So how does derivative action work? From the formula of a PID controller, we notice a third term that has a derivative time constant multiplying the derivative of the error. As the error is rising, the derivative term adds controller output faster than the error grows or the integral action has time to accumulate. This extra derivative kick forces a faster change in the controller output and reduces the peak error. However, on the other side of the error peak, the derivative changes sign, and now the derivative term reduces the effect of the error and the integral action, so the path back to set point is slower than without derivative action. Despite the change, the integrated error under the PID response is smaller than under the PI curve. Let's look a bit more detail at the new process and its dynamics. The new process consists of three equally sized lags in series. Think of three heated tanks in a row where the heater supplies heat to the first tank and the temperature in the third tank is measured and controlled. Since the steady state gain is 1 for this system, we make a 10% step change in the input, we get a 10% change in the output, as shown on the left part of the figure. Even though the response reminds us of a first order lag with a small dead time, that is not what the underlying process is. However, we can attempt to model it as a first order lag plus dead time process, and that model is shown to the right. In the model, the dead time is 0.1 and the time constant is 0.2 hours. While the step response from the actual process and its model look quite similar, there are differences in the dynamics. Some of those can be seen from performing ATV tests on the process and its model, as is shown in this figure. While the ultimate period is almost the same, the ultimate gain from testing the actual process is more than twice that from testing the model. The difference in ultimate gain and the difference in the shape of the ATV response give rise to two very different sets of PI controller tuning parameters. The ones from testing the simple first order plus dead time model are perfect for the model by design actually of the ETL procedure, whereas the ones from the process are too underdamped. To improve the controller response on the actual process, we consider adding derivative action. The benefit of derivative action is to stabilize the loop by removing some phase shift caused by the intermediate lags. In our case, we have three equal lags with a time constant equal to 0.1 hour each. So what is a good tuning strategy for a PID controller? Well, one possibility is to start from the PI controller settings, which in this case for the process is a gain of 2.35 and a reset time of 0.41. Then we can look for an intermediate lag in the process, and in this case we happen to have three equal lags, so we take one of those as 0.1 hours and we apply that number to the derivative time. It also happens to be a quarter or so of the reset time, and that's a good criteria for finding the derivative time. So a possible tuning strategy is summarized on this slide. And the example that I give here is using the derivative time of 0.1 and apply it to the controller settings that we found from the ATV and ETL test. So we have 2.35 gain, 0.41 reset time, that hasn't changed, but now we've added on a 0.1 hour of derivative time. It stabilizes the process. There's less oscillations in the process from the step response or the set point response. So we actually try to increase the gain a little bit, and we can go from 2.35 to 3.4, and we don't see much of a difference in the set point response. However, the benefit of derivative action is clearly seen in disturbance rejection. So here's the same process, and on the upper left is the PI controller with 2.35 gain and 0.41 reset time, responding to a step change in the disturbance to the process. You can see there are some oscillations in there, and we can improve on that. And you see when I added just the 0.1 hour of derivative time, we got a lot less oscillations, a lower peak and less oscillations. And then when I increased the gain to 3.4, I got a much lower peak and a very good and stable response. So we can summarize the benefits of PID control by looking at disturbance rejection. So in the upper left corner is the PI controller that we got directly from ATB test and ETL settings, set 2.35 gain and a reset time of 0.41. To the right of that is the disturbance response with Ziegler-Nichols settings. We haven't talked much about those. Those are the very original settings, but usually perceived to give underdamped and oscillatory response, just like it's doing in this picture here. Below the PI controller is an optimal PI controller that's more stable than the one that I showed directly from the ATV test. And this PI controller is then to be compared and contrasted with the optimal PID controller, where the settings, I showed you before how I got to those, but the settings are so that the robustness is the same as for the optimal PI controller. This is a summary slide of derivative action. It can be very useful for the right kind of loops, but it's not for every loop. A well-tuned PI controller is usually sufficient for most process control applications. But if you have intermediate lags, like thermal wells, temperature loops, and so forth, derivative action can actually be quite useful for disturbance rejection. However, look out for noisy measurements. Flow loops should never have derivative action, and processes with a long dead time to time constant ratio won't benefit from derivative either. Remember, derivative is the third parameter and adds complexity, and the ability to get all three parameters correct is harder than to just get the PI controller correctly tuned. Okay, after this, we will switch gears a little bit and talk about integrating processes. An integrating process is one that keeps changing as long as the input and output are not exactly matched. In other words, if the outflow is slightly less or more than the inflow, the level will keep changing, and either until the tank is overfilled or completely empty. So therefore, buffer tanks must always be controlled, level controlled. Now, fortunately, it's really easy to do that. All you need is a proportional-only controller. You set the controller gain equal to 2, and that means that when the tank is 75% full, the valve is completely open, and when the level is down at 25%, the valve is completely closed. So the level stays within 25 to 75% of the tank, and the flow out is smoothed compared to the flow in. There is one important dynamic parameter that comes into play, and I'll show you shortly how, and that is the hold-up time. So the hold-up time is defined as the time it takes for the tank to be completely empty after being full when the outlet valve is completely open. In other words, start with a full tank, open the valve completely, and wait until the tank is empty. The time it took to empty it is the hold-up time. I said that tuning a proportional-only controller is easy, but sometimes people have this notion that they want to smooth the control of the outflow a bit more than the proportional controller will do. So they would like to have a lower gain on the controller to make it smoother. Now, unfortunately, with a lower gain, you're not guaranteed to have the level stay in the tank with a proportional-only controller. So you need integrating action. Now, as soon as you add a PI controller to a tank level situation, you're introducing two integrators into the system, and you definitely have the possibility of oscillations. So there is a formula, a simple formula, by which you can guarantee that you will not have oscillations in the system, and that is this one here, that the gain times the integral time has to be 4 times the hold-up time. So what does it mean? Well, the interesting thing is that if the gain is low, then you would think that perhaps you can be more aggressive with the integral time, but not so. If the gain is low, you also have to increase the integral time or reset time. in order for this tank level to be non-oscillatory. So I'll show you a couple of examples here. The first one is with a proportional only controller with a gain of 2 to the upper left. You see there are no overshoot in the outflow. The level comes up nicely to a new level after a change in the input flow. On the one to the right, we have a PI controller, and this time I have tuned it correctly, so the reset time being 0.37 hours is correct for that gain of 2, which of course is unnecessary, but it brings the level back to 50% or 40% in this case, which may or may not be necessary to do. So the benefit of having a PI controller would be if you like to lower the gain. So in the next plot here, I have a gain of 1, and now I have to have a reset time of 0.74. So I had to increase the reset time. And you can see now that the outflow is a little bit smoother than it was before, and the level sort of changes a little bit more than it did in the proportional only control case. And then finally, I'm testing with a PI controller that has a gain of a half, 0.5. And in that case, you definitely would need to have integral action, otherwise the tank level would not stay within the tank. So the correct reset time is now even higher. It's 1.48 hours. And you can see that the outflow is quite smooth. The level deviates much more than the proportional only controller, but it is, and it overshoots a little bit, but it's basically stable. So if we do it incorrectly, by mistake, for this controller with a gain of a half, we set the reset time to 0.2 hours. Now you see we introduced oscillations both in the level, but more importantly in the outflow. So if you have several tanks in series, one after the other, which is very typical in chemical process, and you start to have oscillation in one of the tanks, well, guess what? That oscillation will translate down to the subsequent tanks. Not a good situation. So if at all possible, stay with proportional only controller. If you have to have a PI controller for some reason, don't forget to use this particular formula when you tune the controller. Okay, next thing up is flow controllers. Flow control loops are very fast typically, and the measurement is almost equal to the manipulated variable. In other words, we measure flow, we control the flow, same flow. So the gain is typically 1 in the process, and therefore, in order to stay below 1 in the loop gain, you typically have to have a controller gain that's less than 1. But in order to get any type of disturbance rejection or correction, or being able to stay on set point, you have to have a pretty aggressive integral action, and you can have a very short integral time with benefit here. So what's recommended is about 7 seconds, 0.002 hours or so, with a gain of between 0.2 and 0.5. But never apply any derivative action, because that would definitely destroy the loop. Finally, talking about another set of integrating processes, and that's pressure control. So a pressure control situation is kind of similar to a level control situation, except that gases will escape out of an exit valve all by itself just due to a pressure difference. There's no pump needed or anything like that. And therefore, the severity of this being an integrating process is mitigated by the fact that it almost behaves like a self-controlling process, in the sense that the pressure in the tank will reduce by itself, even if the valve setting is not equal to the input flow. But the controller settings, nevertheless, should be such that you can hold the pressure tightly. There is relatively little dead time in a process like that, and it's almost like a first-order lag. Therefore, very aggressive controller action can be applied. You can have tight pressure control with a proportional only controller with a high gain, and that works. And then you can also have averaging pressure control that's more like almost like a flow controller, but in either case, pressure control is also fairly easy to control. So level, flow, and pressure, you don't have to go through ATV tuning. You shouldn't. You should apply the rules that I have outlined here, and you will be fine.